What we're going to talk about, me and my colleague Clement, is the idea that we've come up, which is called Coderules, and that is intended to re-implement our type system design, basically from scratch. Let's start again. And hopefully fix the issues that we are facing with the current design. And this talk is going to be consisting of two parts. First, I do some warm-up, and then Clement will show the details of his Kotlin type system implementation. So I'm going to talk a little bit about the limitations of the current design, the challenges we're facing. Then I will introduce quickly the code rules and explain what it's all about. And then I'll suggest you look at the type system from a different angle and see some patterns that hopefully will provide ideas that we are driven by in this project. So type system design with MPS is basically heavily influenced by Java. And when this, the whole project, I mean, MPS started, idea was still in development. Java didn't have generics. And there were quite a few wild ideas, such as how about represent any programming language as a graph. But later we changed that to H3, AST. And another idea was how about we just enumerate all types, put them into a final lattice, and run various algorithms on this lattice, which makes type system pretty trivial. But in reality, turns out we can't really enumerate all types. So we came up with this Inequation replacement rules as a solution for the problem. And it helps us answer basically two questions. So what conditions should be that A subtype of B is true? Or if we have a parameterizer type with some inference variable alpha, what should be the value of this alpha so that, again, A of alpha is subtype of B? Right, and problems we run into with equation replacement rules are various, and I will just name a few. First of all, is let's imagine we have just simple hierarchy of types without, we don't care about their structure. We just know that B is subtype of A, C is subtype of B, and all this is defined using replacement rules. Then actually to solve inequations such as C is subtype of A, we need to introduce it explicitly. Okay, we must enumerate all the possible combinations. And then when we create a new type, D, which is subtype of C again. So this goes on and on. Another problem we face with replacement rules, heuristics that unfortunately have to be applied in some situations. With me type, it's easy. Okay, we just check all the subtypings, and with union, there is no an easy way to solve it unless we just pick one at random, or we use some heuristic, because otherwise it's unsolvable unless we have backtracking, and we don't have backtracking. Now, slightly different topic is the LUB, the least upper bound. And you probably know the type of this So let me try. Works. Okay, this strange expression, which is question mark, string, and integer. The type of this expression is some kind of intersection. So how this algorithm works today? We take our finite lattice and run a simple algorithm on it, eliminate some subtypes, and then when we find types that are not related to each other, we just make intersection, which results in, unfortunately, in something. But well, okay. When we take a list of strings, a list of integers, and take and try to find this LUB, and the real type has to be this. Quite complicated. MPS only comes up with the question mark without any bounds. Yet another topic is when inequations are really solved. Inequations needs to be solved in order to find the values of inference variables. And it's on the surface, it's easy, right? We just if we have only one inequation, we use it to assign the value. If we have two or more, we take a intersection again. But there's a problem. It's not defined when exactly those inequations are solved. And this can lead to situations like the following. We have two inequations, A subtype of B, A subtype of C. A small a is here is an inference variable. Should be alpha. But in case we first encounter the equation A is subtype of B, we'll just assign A to B. But then another an equation comes, which results in an error because B is not subtype of C. But when we have them at the same time, when we try to solve them as a system of inequations, we just build an intersection and have no problems. So as a recap, these are the major issues type system designer faces with the current implementation, and what we're trying to do is to deal with these. So now I try to introduce code rules, constraint processing system. Why? Because we wanted to try something. We didn't know how to deal with the various issues we faced. We didn't know how to fix our type system, so it type checks Java, basically. And we took constraint handling rules, this theoretic abstraction, which is inspired by Prolog, and it has existed since a quarter century already. And what we added is the unification of terms in pattern matching and also logical variables. Then, to explain what code rules are, we first need to define what constraint is. But there's no simple way to do that either. On the surface, constraint is data class. That's its implementation. You can think of a constraint as a row in a database table. Because it has some arity, and every position of its argument means something and has its type. Basically, it's a tuple, but with a symbol. Right, so we can think about constraint as either predicate or a fact or assertion, query, depending on the context. How we use it in our implementation? We use constraints to represent relations, such as converts to, which is analogous to subtyping, or contains in, which is another kind of relation that doesn't exist right now. Or we can use it to just evaluate some program and find the value that we're interested in. As an argument, we can use any Java object, provided it has equals in hash code as usual. So this is a very generic scheme of what a constraint rule looks like. It's had the head consisting of 3 clauses. So given this list of constraints, we solve another list of constraints. We get rid of them when guard condition is satisfied. And as a result of firing this rule, we activate the list of constraints in the body. And there's also else. Else means that if we encounter error during evaluating of the main body branch, we can recover with evaluating what's in else branch. So this is the constraints life cycle. They are first activated. If the activation leads to an error, we fail the rule unless there is an else branch, which sort of catch and try. And if a constant is not solved, it's stored for the future in something called constraint store. Now, let's look back at the type system that we have. Let's think of it as a system of constraints. For example, equation replacement rules, they are very similar indeed to a constraint rule. They solve relation, they have some kind of condition. The difference is we don't have backtracking, and there is no easy way to extend or override. But although that is work in progress, and I think somebody mentioned it already that we have a feature request for that. Comparison rules, same logic applies here. Basically, what they are doing is checking a few conditions, and can be easily implemented as constraint rule. Operation overloading rules, again, when we have the type left and the type on the right, we can just apply a case, switch, and find the type of the whole operation. That's kind of clear. Our existing operations are easily mapped into constraints. So subtyping becomes converts to. This tilde operator becomes comparable to another kind of constraint. And equation becomes just unification of terms. We have new aspect defined for language, which can contain roots of these rules, macros, terms, and queries. And the main fundamental thing that this type system consists of is rule templates, which are organized nicely into lists, and the order of constraint rule templates in this list matters because they are applied exactly in this order. And those lists can be extended, can even be overridden. This is a very simple or trivial example of rule template. the whole thing is a simple rule, which is very similar to inference rule. It's applied to an instance of dot expression. It contains simply a list of base language statements. This keyword on defines a special statement that results in creating this kind of rule, which is called in this case it's a very simple propagation rule that says when we have the type of the operation, we know the type of when we have the type of the operand, we know the type of the whole operation. And type system with code rules works as a two-stage process. First, we analyze the code, produce code rules program, but don't activate the constraints yet until we analyze all the code. And then we launch this code rules program, which is, well, strictly speaking, it's a programming language. It's in its own right and has well-defined semantics. So this is a recap. I hope that is understandable. And as a summary, what's the difference to the existing type system design? We drop enumeratable supertypes. We resolve all relations explicitly using rules. And rules can be easily extended or written. And we hope that the result will be a cleaner and easier to understand type system for your languages. Thank you so much. This is the end of my part, and Clement will take over.
Thank you. Okay. All right. So in my part, I will briefly introduce you to the Kotlin type system in MPS and how basically it was implemented using code rules. So there will be two parts to this presentation. I will first give some more details about the constraint system, how it operates, and then I will basically give you an overview of the Kotlin type system, and then give you some insight of how it's done, like few subsystems implemented, basically. So constraints, Fedor already introduced them. Basically, you can define any kind of constraints you want. You can give them any kind of type. You have this term type that is specific to code rules, which allows for matching, but we're not going to cover that too much. There is one thing that should be known is basically code rules provide no constraints by default. Every constraint that you would use in your type system would be defined by you if you use, well, your own language. For example, if you extend another language, of course, you would use the constraints from this language. So, well, yeah, these are three examples of constraints that you can find in a type system. So you have constraints about types, conversions, and so on. And those, as mentioned, are just data to code rules. So they do not mean anything on their own. And for meanings to be added to those constraints, you basically use rules. So for example, when you have such constraints, so basically code rules operates on a set of constraints. So it's kind of the state of the program. And on every step, it will basically apply rules that are applicable, to transform this state into another. So if we have the following rule, so it's a really simple one. It basically has no, complicated features inside. You basically match on two constraints, so it's the head. If it matches the program state, in this case, it's a perfect match. Then the rule is activated. In Coderules, the replacement are marked with this tilde character. So everything that is going to be replaced is removed from the state when the rule activates. And then we basically take what's in the body and insert it into the state. So you end up with this final state from this initial state. And since we inserted a new constraint, well, maybe there are some other rules that would allow to, well, make further operations. So basically you can insert a rule at the beginning, a constraint, and then you would get some rules that would expand the program to a lot of constraints. And in the end, it would reduce down to the results that you need. So let's move on to Kotlin type system. So here is a short overview, or some overview of all the subsystems you can find in the type system. You can mention subtyping, type rules, also type constraints. We have in Kotlin used for smart cast analysis because the types are basically inferred differently than in Java. You don't want to introduce variables when you are casting, for example. You have some need for overload resolution, so it's when you want to find which function is appropriate for a given function call. So if you have, for example, conversion from, a few arguments and you have few overloads of a function, you want to know which one to choose. And this is something that relies heavily on the type system. And which brings me to some issues there, because in the legacy type system, we can see in red here are the parts that basically are provided. So this is things that we cannot really change or control. You have some APIs, of course, to influence on that. For example, if you take type constraints, you can insert any kind of constraint. But when you want to trigger them, well, you do not have any control over that. So you cannot choose when to trigger the constraints, which constraints to trigger, and so on. So all these parts in color, in Coderules, they need to be implemented again for a given language, for example, Kotlin. And you basically have in your type system a set of subsystems that would have some constraints to provide input and also to get results from this subsystem. So it's all defined in Coderules, but you can have several sections, if I'm clear. What else to say? So the Kotlin specification is fully available online. You can check it out. It contains mostly all these parts that are fully described. And now we're going to look into some subsystems and how they are basically made with Coderules. So the first one we're going to look into is type constraints. So basically to provide, to use type constraints, you need to insert them. So you have a Coderules constraint, which is named constraint, quite confusing. It contains a subtype, a supertype, so basically the same as we would have in the legacy type system. And on top of that, you can declare a few things. So you have inference variable, which allows to mark something that is undefined as an inference variable. You can specify a pool, so whether you want it to be solved with regard to upper bounds or with regard to lower bounds, or both. And you also have something very interesting here, which is a scope. And in comparison to the legacy type system, where you couldn't choose what would be solved, well, this scope object basically allows to group variables together. So if you are working, for example, on a statement, and you don't want to solve the variables outside of this statement, well, you would use a specific scope for this statement. So basically, it allows to have a fine control over resolution, which is triggered by the two constraints there. You have resolve scope and resolve var, which allows, to resolve all the variables in a scope or just one variable. So you basically can insert them anytime in your program, and there is nothing that decided for you. So if you don't do it, well, it won't be done. We also have some tools over types. So we mentioned list upper bound for the legacy type system. In the legacy type system, it was implemented as in, so you couldn't really access it. But here in Coderules, it's another constraint that you can use. You can extend and you can basically process with your own custom rules. So if you have a language that needs a specific processing in this list upper bound, you can basically add extension for it. So let's show, I'm just going to show you some rule that is used in this subsystem. So basically when we insert constraints, there are some steps to basically get to something that cannot be reduced. So you get from, for example, a constraint over 2 function types, and you want to make sure that, well, this holds true. So you basically reduce it to another set of constraints. So you know that function types convert together, but only if their parameters and return types matches. So then you basically introduce new constraints. So you have a constraint list, which gets reduced further to constraints and constraints on the return type. So it's basically one step of this constraint subsystem. Basically everything, well, you can, if you look into the type system, there are many of them, and it basically takes well, slowly, by small iterations, it gets you to the result that you need. So another thing that's quite important is the type checking. So in the legacy type system, you define inference rules, which allow to check, well, the types of a node. In Kotlin, basically in Coderules, you define that on your own, so you can have your own assumptions. And one thing that's really important here is, well, if you use the legacy type system, you can assert, for example, if the type of a node is defined or not, but you are not really sure if the type is set or unset, if the rule that processes this type has been fully triggered. So if, for example, you check the type of, you get the type of a node, and this node is waiting for some other type, well, when you are getting this type, you don't know basically if the wait for that other type has been done. So you might end up in situations where you might get the wrong state, and that's what's actually the issue about time constraints resolution, and why it's important not to resolve too early or too late. You might miss constraints or have constraints that you don't want. So it's quite important, and basically in Kotlin, in this type system, it was done in a way that we are not, well, we basically can get this state, we can know if a rule has been triggered and processed, and that's the basic principle of this type checking. Basically, every entry point goes from the get type constraint. So when you want to get a type of a node, you use this, and this will ensure you that the rule has been triggered and processed. And how it does it, it basically triggers a compute type constraint, which is basically the entry point for any rule. And it also stores some kind of cache if you want to, for example, call multiple times the type of a node. You want to make sure that you're not recursively checking that. You also have some toCheck constraint, which allows to basically add some kind of optional dependency. Because, for example, if you want the type of an if expression in Kotlin, you don't really need to check for the condition. There is a check process for that, and during that, this check process, these will be checked. So another rule here, this is the Elvis operator in Kotlin. So you have a left expression, and if it's null, you want the result to be the right expression, basically. So how it's done, we get our entry point, so compute type, that's basically when a rule starts. And then we get the type of the left and the right expression. So it's very similar to the legacy type system, except that this time we are actively triggering the resolution of the left and right type, because these constraints will trigger the rules. Then we get some operation on type, non-nullable type, basically remove any kind of nullable markers. and you reuse here the list upper bound that we saw before. So we basically take the left and right type, and the result is a unification of those types. All right, so I'm gonna show you now a simple demo of this, live. So I'm gonna move to this. Okay. So we have this simple function in Kotlin. It basically takes an expression, and if it's an integer constant, it basically gives the value. Otherwise, it gives not a number. So it could be used like that. One thing to note here is this is actually a node expression. So there is a short notation in Kotlin, but you can use this notation. I'm not going to go too much into details, but the implementation is different, and you can basically use type parameters as freely as you would in any Java class. So it's more convenient in a way, though it's even worse when you read it. But we're not going to go too much into that. Basically, what we want to know is how things are processed. So we have here some messages from Coderules that tells us, okay, we are checking the sample, which is the name of this root node. There are some convert operation there, and some other operation we're gonna see later, maybe, if we have time. I'm just gonna trigger it again. So if we look here, we can basically show the trace of what's happening. And basically you can see here the full tree of what's happening inside the type system. So everything starts from the check constraint. I didn't introduce it when it was on the slide, but it's basically what begins the program. So basically we have queries here, which is the entry point of any Coderules program, and basically it activates, right. It basically, I think this one is the one of base language, but anyway, it's where all the beginning constraints are introduced. So this is the beginning of your program and what gets things started. So that's there. Why is it? Oh, sorry. So we basically start from there and then we expand. So this is, base language. There is something that basically allows multiple languages to operate together, but it's implementation detail. So the first thing we are going to do is check this function. So this is the entry point. Basically, there is a rule here that checks every entry. So it's called a data flow source here, but it's not so much related about data flow. And it basically triggers the entry points. So for example, functions, parameters, and so on. We can see here that triggering this check basically cause a get type here. Here we have get type of our own function. So it's described there. And then we have some recursion guard, and we actually go into the function declaration. So you can actually see the process as it goes. You can access here the template. So you see that we go from compute type, we get some operations, and it's a lot of it's a complex template, so I probably don't have time to explain it all. But yeah, you can basically see the whole process as it goes. And what's interesting here is you have on the right side the list of the state of your program, the list of constraints that are present. So for example, if we look at this point, so any point in the program, we have two types that are defined. So these are the constraints that are used as a cache. And you can see that with data, so I guess data is this variable, we have a type here, which is a node type with the type of an expression. So probably, it's the first data. And so basically you have all the process happening there. And you can debug it. Any questions so far? Okay, so I'm just going to conclude a little bit on Yeah, there. So yeah, thank you for your attention. I'm gonna conclude. Well, basically, here you have all the links to get to this Coderules type system and also the Kotlin type system. You have access to references, documentation, and so on. This is still a work in progress. I didn't mention it too much, but currently, there is need for data flow analysis, and this is done currently with Coderules. So we are not using the data flow aspect currently, which is probably a mistake because it's a different implementation. Yeah. In the future, anyway, it's going to be using the data flow aspect. So which is going to get the type system much simpler because the current state, your type rules also process the data flow, which is quite difficult. You have basically some refactoring happening, and that's it. Yeah. So if you want to try out the Kotlin type system, we'd be happy to get your feedback as well. Thank you. Any questions?
Do you know anything about the actual Kotlin type system? I mean, the language that's not implemented in MPS, but in the Kotlin compiler. Do they also use a similar approach?
Well, I know that they use some, I know they implement it in Java, basically. They're not, I don't think they are using any constraint system. But I based my whole work on the specification of the language, which basically defines how the full type system is defined. So most of the process there are looking quite similar to what's done in the internal Kotlin type system. But the implementation is, of course, different.
Roughly how much time or work went into this, and what are challenges or things that you couldn't solve more or less elegantly?
Well, I spent, I think, quite almost a year on the type system. The reason for that is basically I was the first user of Coderules as well, so it's something that basically wasn't documented or, well, not fully easy to do. And yeah, also because there was no patterns before, like how to do things.
Well, I could add something to this. If we're talking about efforts that went into the whole project, Coderules and Kotlin type system, that was quite a lot. And that was because at some point of time we've taken what I would call a wrong route, and we had to rewrite basically a big chunk of code. And yeah, also not seeing progress for a long time has its impact, and we're not paying too much. We're not putting into too much effort into this now, and basically we were thinking about releasing it when we have support for Kotlin. Although we have support for base language, extensions and all the languages in MPS as well. Maybe not in a fully finished state, but still.
So in earlier demos years ago, I think I saw the use of something that reminded me of kind of quotations, where you were like programmatically constructing the constraints, which were then executed. This is gone, right? This is now done with these function-like syntax. You know what I mean?
Not exactly sure. The constraints are created with sort of DSL, which is sort of quotation, yes.
Okay. Mm-hmm.
Maybe it looks different because we changed the syntax.
Maybe this is.
This thing is not a constraint. This is a term. And term is an object that we use to represent types.
Yeah, okay.
It's just a simplified version of a node.
Okay.
Any more questions? I guess not. So